So today we're going to dive into the physics behind that heart in your throat feeling you get on a roller coaster. You know, the climb, that little pause at the top, and then the big plunge. It's really just a dance between two basic types of energy. Potential energy, which is all about position, and kinetic energy, the energy of motion. And once you understand how they trade places, you'll start seeing physics everywhere.
Just think about it. That slow, click-clack-click climb to the very top, the moment of complete silence, and then that incredible rush all the way down. Well, that whole experience, it's a perfect real-world example of energy just changing its form right before your eyes.
So here's what we've got on tap. We'll kick things off with potential energy, the power of just being somewhere. Then we'll get things moving with kinetic energy, the power of motion. After that, we'll see how they swap places in what I like to call the Great Energy Exchange. And finally, we'll put it all to the test. So let's jump right in. Okay, first up, potential energy. You can pretty much just think of this as stored up energy. It's the energy an object has, not because it's doing anything, but simply because of where it is, just waiting to be set loose.
Now, the one we're really going to focus on is gravitational potential energy, or GPE. It's the energy something gets just by being inside a gravitational field, like right here on Earth. Basically, anytime you lift something up, you're fighting against gravity, and the energy you use gets stored in that object. The higher you lift it, the more energy you pack into it. Take a look at this. It's a super simple example. As this person stacks these tins, they're literally doing work against gravity. And that work doesn't just vanish. Nope, it gets converted into gravitational potential energy, and it's stored inside each one of those tins. If one of them falls, well, that's the stored energy being released.
All right, let's head back to our roller coaster. To figure out its GPE at the top of a 30-meter hill, we just need to plug the numbers into our formula. So we take the mass, which is 500 kilograms, multiply that by gravity's pull, 9.81, and then multiply by the height, 30 meters. And what do we get? A whopping 147,150 joules of stored energy, just sitting there, ready to go.
So, that's all about stored energy, but what happens when you finally let it go? Well, that's where kinetic energy comes in. You could say if potential energy is all about what could happen, kinetic energy is what's happening right now. It is the energy of pure, simple motion.
Yep, anything that's moving has kinetic energy. The two things that decide how much it has are its mass and, way more importantly, its speed. And as you're about to see, speed has this huge, kind of magical effect on an object's kinetic energy.
And wow, this right here is a perfect illustration of kinetic energy in action. A pile driver gets lifted way up high, storing a massive amount of potential energy. The second it's released, all that potential energy starts converting into kinetic energy as it picks up speed on the way down. It's that incredible energy of motion that lets it slam a pile deep into the ground.
Let's run a quick calculation. Nice and easy. For a 2-kilogram object moving at 3 meters per second, we just use the formula. That's 0.5 times 2 kilograms times 3 squared. Well, 3 squared is 9, so the answer is a simple 9 joules of kinetic energy. Easy, right?
And this, my friends, brings us to the really cool part, how these two types of energy are connected. It's like a constant dance, a trade-off, where one goes up as the other goes down. And the whole thing is run by one of the most basic rules in all of physics. So let's put them side by side. You've got potential energy, it's stored, and it all depends on height. It's at its absolute maximum when something is way up high and not moving, just like our roller coaster at the very peak. Then you have kinetic energy. It's all motion, and it depends on speed. It's at its max when the object is moving the fastest, which is usually at its lowest point. Here's a fantastic example of this whole transformation. Imagine you have a weight on a stretched-out vertical spring. At its lowest point, all the energy is stored in that spring as elastic potential energy. The moment it's released and shoots up, that elastic energy turns into kinetic energy, the energy of motion. And then, as it reaches its highest point and stops for a split second, that kinetic energy has been transformed into gravitational potential energy. It's a perfect 3-act play of energy conversion.
And this all comes down to one simple idea, the law of conservation of energy. Basically, in a perfect world with no air resistance or friction, the total amount of energy never ever changes. The potential energy an object has at the top gets completely converted into kinetic energy at the bottom. This gives us this amazingly useful equation, mgh equals 1/2 mv squared.
All right, enough with the theory. It's time to see how all this works in the real world. Let's crunch some numbers and tackle a few problems to make sure this all really sinks in.
Here we go, first problem. We have a 900-kilogram car moving at 20 meters per second. So we grab our kinetic energy formula, 0.5 times 900 times 20 squared. That gives us 180,000 joules. But here's the kicker. Where did that energy come from? It was converted from the chemical potential energy that was stored in the car's fuel. See? Energy always comes from somewhere.
Now for a GPE challenge with 3 different scenarios. We need to find the change in potential energy for a person climbing, a book being lifted, and a plane coming down for a landing. Now, pay attention to that last one. The height is decreasing. What do you think that's going to mean for our answer? Okay, let's look at the results. The person climbing gains about 13,000 joules of potential energy. The book gains just a tiny 12 joules. But now look at the aircraft. Because it's coming down, its change in height is negative. That means it loses 2.4 billion joules of potential energy. That energy is being converted into motion and a whole lot of heat as it lands.
All right, time for our final challenge. This one is all about kinetic energy, and it's designed to show 2 really important things: why units matter and the crazy effect that speed has. We've got a car doing 100 kilometers per hour and a cyclist who doubles their speed. Let's see what happens.
So first things first. Before we can even touch the kinetic energy formula for that car, we have to deal with the units. Physics formulas demand standard units, which means we can't use kilometers per hour. We have to convert it to meters per second. So 100 divided by 3.6 gives us our real speed, 27.8 meters per second. This is a critical first step, and it's so easy to forget.
Now that we have the right units, we find the car's kinetic energy is a massive 310,000 joules. But look at what happens with the cyclist. This is the really mind-blowing part. At their starting speed, they have 1,000 joules of energy. But when they just double their speed to 10 meters per second, their kinetic energy doesn't double. It jumps all the way to 4,000 joules. That's the big takeaway. Because speed is squared in the formula, when you double your speed, you actually quadruple your energy.
So let's wrap this all up. Here's what you really need to remember. GPE is stored energy, and it's all about height. KE is motion energy, and it's all about speed. Energy is always conserved. It just transforms between these 2 states. And don't ever forget the incredible power of speed. Double the speed, and you get 4 times the kinetic energy.
And in the end, this all comes back to one of the most fundamental rules of the universe, summed up perfectly by the first law of thermodynamics. Energy is constant. It just changes its costume, transforming from potential to kinetic and back again, driving absolutely everything you see.
So, I'll leave you with this thought. Energy is never lost. It's only ever changed. Whether you're looking at a bouncing ball, a flowing river, or even a shooting star, this great energy exchange is happening all around you, all the time. The question is, where are you going to see it next?